And welcome everybody to our official start of data structures for today. Today, I think is going to be, at least for me, it's going to be an exciting class. So again, we're talking about this binary search algorithm today in class. Last time we started talking about recursion, and we were looking at kind of toy problems with respect to recursion last time. We saw this factorial problem and this sequential search problem. And we saw both of those in both an iterative implementation. So iterative meaning using like for loops or while loops. And then we also saw the recursive implementation, and recursion meaning that the function somehow calls itself in the middle of the function. And both of those algorithms are actually things that, even though you can use recursion, most people would probably use for loops for them. That for loops tend to be easier, both from an implementation perspective and from a runtime analysis perspective when you're able to use them. But today with binary search, we're going to see our first sort of real algorithm where recursion really shines. And it shines in two ways. The first way is that it's actually much simpler to explain and think about recursively. But it also is actually much easier to do the runtime analysis as well. And actually with loops, there's no way to do the runtime analysis at all. You have to use recursion in order to do the runtime analysis of binary search. So that's kind of the motivation why we were talking about recursion last time. We'll see the application this time. And this binary search algorithm, again, is sort of like the key computer science, like foundational key concept. The one thing to take away from this class is how binary search works and why it's important. Again, it's sort of like the key background algorithm about how, say, Google search works and how you type in your web query and it's able to find, search through billions and billions of web pages in fractions of a second and give you great results. Anything where speed is of like the essence in computer science, it always comes down to some variation of binary search. Because of that, so it has lots of applications in the real world and in interview problems. If you're going on a technical interview at any of the major tech companies, Microsoft, Facebook, Google, any of these companies, you're going to have a question that is somehow involving binary search. It might be kind of in disguise in a little bit, but there will be something that you'll have to talk about binary search with. So this is, for lots of reasons, very important lecture today. And if you do have any questions, definitely interrupt and ask them. You all have been great so far about asking questions. Just keep it up for this lecture. It's extra important. Okay, so let's see, that's our big picture overview for today. I have a couple of quick announcements that I want to do before we actually get into that material though. So I'm going to share my screen. And currently I have our class repository pulled up on week 4. And actually I want to go back real quick to week 3, to last week's word ladder assignment. All of these assignments, at least that have been submitted so far, have been graded. And I just want to point out down here, there was a mistake in this write-up for the tasks about how the assignment was going to be graded. That I had originally put your grade will be the percentage of test cases that successfully pass in Travis. And this was from an old version of the assignment when there were actually only 5 test cases, the really, really hard test cases. But I decided to make the assignment a little bit easier by adding more test cases for you to work with to make development an easier process. And so because of that change in test cases, the actual grading is -1 point for each failing test case. And so if you got to a point where on your assignment where you didn't fully complete all of the test cases, but you were okay with what your grade was based on this grading rule, know that you were actually graded on this grading rule instead of this one. Because I had this typo here though, I don't want you all to be penalized for if you were following what the instructions actually said. And so anybody who, well, anybody in the class who wants to resubmit your assignment, you have until Friday of this week, sorry, until Sunday of this week. So essentially a full extra week to work on it, to get whatever test cases that we're not passing, get them to the point where they are passing.
Mike, sorry, kind of a tangent, but what is Travis?
Oh, good question. So Travis is a continuous integration tool, just like GitHub Actions is. And so yeah, this sentence actually came from last semester's version of the class. We were using Travis instead of GitHub Actions. The reason for that, or the reason that we switched away from Travis to GitHub Actions, is that Travis started charging money and GitHub Actions is now free. So wanted to keep the course free for everybody. You don't have to purchase anything. So switch things over to GitHub Actions. And looks like I forgot to not only change this whole sentence, but change that word right there as well. Great question. Any questions about that policy for this word ladder homework? Okay, I posted 2 issues as well that I want to just highlight. So this first one is kind of related to this grading policy in this course, and it is a fairly strict grading policy of that one test case corresponds to 1 point. By the time you're getting to the point where most of the test cases are passing, you've already put in a lot of effort into the assignment. And so it might feel like, oh, I've gotten everything, but I've gotten like, there's 40 test cases, I've gotten 35 of them to pass. That should be a relatively good grade, but it's missing 5 test cases, and so that's a 50%. Maybe at first that doesn't seem fair to you, but I want to highlight that the reason for this sort of harsh grading policy is because perfect software actually really is important. And so in this example right here, this is a recent news article just published this week actually. And what was happening was there was a computer program used by Arizona's Department of Corrections, so the state department in charge of prisons and jails. And this computer program was used to determine when prisoners should be released from jail. And in this code, there had about 18,000 test cases that were known to be failing. And they still ended up deploying this code and having it determine when prisoners should be released or not released. But even though this code was buggy, the people who are not software engineers using this code, so police officers and prison officials, just kind of saw that, hey, the software said this person should still be in jail, so I'm just going to leave them in jail and not release them, not understanding that software can be buggy. And in general, people who are not computer programmers have this tendency to assume that if a computer program says something, it must be correct, and believe it without faults. So this is a case where these failing test cases have resulted in thousands of person years of people locked in jail, and they should have been released according to their sort of due process rights. So if you're interested in that, details of that story, there's a link there. You can read all about it. That's just one of the examples of situations where actually correct software is critically important, and just like 95% correct is really not that good. In some senses, it's even worse than nothing, because if we didn't have this jail software, then those people still would have been released. But the fact that we have this jail software and it's buggy means that those people are stuck in jail. So that's one announcement. Another announcement is that I've just posted some details about research opportunities that you all would be really qualified for working on with me. I have a few other posts or other research opportunities I'll be posting later in the semester as well. But this one specifically about big data, scraping from the web, extracting information from web pages, And there's a library that I'm working on that you all would be able to help me out with. And if you're interested in that, there's some videos right here that you can click on and see what those instructions are.
Hey, Mike, quick question.
Yeah,
If we
go ahead.
can we work on this with another person, say if we were interested in it, can we create like a little collab?
About the research opportunity? Yeah, so there's be very excited to have you all collaborating together on the research opportunities. Let's see, I don't think I have a link actually here to the project repository, but it's github.com, Mike Isbicki, meta HTML. And sort of the standard way that I'm assuming that I'll be collaborating with students specifically on this project would be through the issue tabs on this project. So yeah, if you have questions, that would be the place to put it. But definitely it'd be awesome to have if you're working together with other people. Yeah, one of the sort of goals of this course is to get you all sort of familiar with the open source pipeline of how do you contribute to open source projects. And that's what this extra credit opportunity or this research opportunity is contributing to an open source project. And so because it is tied directly into a class goal, you can get extra credit for doing that. So 2 points for just standard pull request being accepted. If you are working with other people, then everybody who participated in that can get those 2 points. If you're doing something a little bit maybe more detailed than that, and there's, again, details on what that means in this video, then there's possibilities for extra points as well. Yeah, if you do have other questions about research stuff, I'd be happy to answer them later or in office hours. But does anybody have questions about that right now that I might be able to answer? Okay. Yeah, I realized that we didn't even really talk about exactly what the details are of the opportunity. That's what the video is. So totally makes sense that there wouldn't be a lot of questions because of that. Okay, so announcements out of the way, time to talk about binary search. And again, this is sort of the last topic of the week here, binary search right here. And we're going to spend a lot of time on this binary search and understanding its runtime analysis. And I'm totally okay if we don't finish the discussion today. If there's lots of questions and we finish it on next week, perfectly fine. So please ask questions. Very important topic today. Okay, so I'm going to switch my screen over to having a little bit different setup today. On the top here, I have just a terminal window open to the week 4. And I'll open up that notes.py file that we've been talking about on Monday. And so far, we've gone through this factorial function here at the top, and then we were talking about this sequential search function. And now what we're going to start looking at is this binary search function. And there's 3 versions of this binary search, this iterative version of binary search, and then there's 2 recursive versions. This one right here is the one that you'll want to use as the basis for your homework assignments. Modify this one right here. It's sort of the most straightforward to modify for the all the homeworks and get the runtimes to be correct. But we're going to start with this one right here, talking about it, since it's the simplest to describe and has the shortest code. If we look at it, it just has like, what is that, like 8 lines or so of code. And I'm going to temporarily have us delete this string right here so that we can see the whole function definition at once and not have to scroll up and down. And then down here in the bottom, I just have a window open where I can write things by hand. And what I'm going to do is, rather than using Python tutor to walk through how this binary search works, we'll work through it sort of by hand down here. And I'll do it in a slightly different way than Python tutor does. And so I would recommend at some point taking this code into Python tutor and stepping through it and just making sure that you really fully understand what's going on in this binary search code. It's again sort of like the foundational algorithm of computer science. So any time you spend like focusing on this algorithm will pay off throughout the rest of the semester hugely. Okay, so in this binary search, we have two parameters, this XS and this Y. And one of the things about binary search is that this list, this XS parameter, has to be sorted. So with the sequential search, there is no requirements on the input list here, but for binary search, it must be sorted. And so I'm going to write out an example of a sorted list down here. So we'll start, say, with -10, and then -3, 1, 5, 8, 16, 17, 18, 23, 25. And these are just a bunch of values that are in the list. And then up above in orange, I'll write the index into the list. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so there's a total of 10 items in this list. And then, so what binary search is going to do, right here is our base case, line 189, checking to see if the length of our XS variable is equal to 0, then return false. In this case, so this whole thing right here is XS, and so it's not equal to 0, the length's not equal to 0, it's equal to 10, and so we're not in the base case yet. And here we have on line 194 and 196 are two recursive calls. And if you remember, there's these laws of recursion that we mentioned last time. Every recursive function has to have a base case, so check, we got that. And the recursive calls somehow need to move us closer to the base case. Or in other words, they need to make our problem smaller somehow. And here, these recursive calls, the way they make our problem smaller is we have our list, XS, and we're somehow, this is called a slice of the list, slicing the list so that we get a smaller list. And eventually we keep slicing it until we hit this base case where there's nothing left in the list. So that's just, anytime you see a recursive algorithm, a good thing to just do a sanity check of those two laws and make sure that it's conceivable that the algorithm is correct and is going to terminate. So now let's think about like what the algorithm's actually doing. The first thing is here at mid, calculating the midpoint of the list. So length of XS divided by 2. This double division sign // that does integer division. So here 10 divided by 5 is always, 10 divided by 2 is 5, is an integer. But if we had 11, 11 divided by 5 would be 5.5. We want our midpoint to be an integer that we can index into the lists. So it's doing this integer division. It's going to round it down to exactly 5 instead of 5.5. And that's the difference between the double slash and the single slash. So the midpoint is going to be 5, this position right here. And we'll go ahead and call that mid. And then what we're going to do is check to see whether the value that we're looking for, this Y value, is either bigger than this midpoint value or less than this midpoint value. So let's say that for our particular problem right now, we'll have Y equals to 1. And so our goal is to check whether 1 is contained in this list. And because I know this list is sorted, So here's the key spot where I'm using this assumption about the list being sorted. Because I know this list is sorted and 1 is less than 16, I know that I do not have to look anywhere over here for the value 1 in the list. I only have to look to the left-hand side of this mid element. So on line 193 right here, we have XS at mid, so that would be 16, is greater than Y. Well, it is in fact true that XS at mid is greater than Y. So I'm going to search in this section over here. When I do XS of this slice right here, colon mid, this colon syntax, when there's nothing to the left of it, it means we are going to take the list from the very beginning, so from the very beginning index, and go up to the mid index, not including the mid index. So here we're not including the 16, and that's okay because we said that y is strictly less than mid. So that means y is not equal to 16, it's something to the left. And we'll search just this section over here. The sort of key magic about this binary search is that in this one iteration, I'm not eliminating only a single value from my things that I'm searching through. I'm eliminating all of this over here. So in the sequential search, I went and could only eliminate one particular position at a time. But with binary search, I can eliminate so many things at a time. I can eliminate half the data at a time. In this case, I'm eliminating the right half, but if it wasn't the right half, then I'd be eliminating the left half. So you can always eliminate half the data. And that's the key magic, the key thing that makes binary search happen. And the key thing that you should be looking for when you're ending up creating your own fast algorithms based on binary search is how can you eliminate not just one element at a time, but try to eliminate half the elements at a time from your search.
Mike, so is the reason it's called binary search because you're splitting it into those two parts, greater than and less than the mid?
Exactly. It's called binary search because you split it into two parts and you only go down one of those two parts. There's an alternative algorithm called trinary search where you split it into three parts and only go down one of those three parts. And we will see later that actually trinary search is no faster than binary search. They have the same asymptotics. Binary search is somehow the simplest way to do this. It doesn't matter whether you're splitting it into 2 parts or 3 parts or 10 parts. Just the fact that you're able to eliminate a big chunk instead of one thing at a time is the key thing. Great question.
I have a question. Is this only for numbers or like I mean, I'm guessing you could do it with strings if you sorted.
Yeah, great question. So here I have our example being numbers just because that's easy to write up. But anything where you have comparison operations available. So strings, you can order strings alphabetically and have comparison operations that way. It turns out that it's possible to have comparison operations on really complex things, like for example, images. There's a way to define like, is one image less than another image or greater than another image? And if you can do that, then you can do binary search on images too. So the key thing here is that we just need to be able to compare two elements against each other to say whether they're greater than or less than. Actually, yeah, so I've mentioned before that like the way Google search is so fast is it uses binary search. And the sort of interesting part about Google search is how they define when one web page is less than another web page. That's sort of like the magic that makes it happen. The algorithm for binary search that they use is exactly the same as this algorithm that we're looking at. They just have a special way of defining when one web page is less than another web page. And we'll talk about some examples of those like clever ways to compare things later on. But for now, just know that you can do other things besides numbers, but that's our example. Great questions. Any other questions so far? Yeah.
Where does the y equals 1 come from?
Good question. So here, this xs and this y are both just passed in as parameters to the function. So y equals 1 is just add me as the user of this binary search function. This is the thing that I want to search for. So it's not part of the algorithm. It's just something that I happen to pick as an example.
Okay, thank you.
Great questions. Any other questions so far? Sam, go ahead.
Would it be faster or slower if you divided up the list into 3s instead of 2s each time?
Yeah, so we'll talk about runtime here in a little bit in detail, but it turns out to be exactly the same. There's no advantage and no disadvantage from a runtime perspective of dividing it into more than 2 segments. I guess there is a disadvantage from a coding perspective because then your code is more complicated. So that's why people always do binary search in practice. But from a runtime perspective, there's no difference. Okay, so here we now have a smaller list right here, and in particular a list that is half the size. And so we're going to recursively call binary search on this this same list, or sorry, using the same function, but on this smaller list now, this list underlined in red. And so when we do that, we'll have to calculate a new midpoint value. So scroll back up here. Sorry about that. And we'll calculate, there's the cursor. So draw a line here just to separate the iterations. We'll calculate a new midpoint value. So for xs colon mid, this new list right here, the length of this list is going to be 6. So in my second iteration, the length equals 6. And so the midpoint value will be equal to 3. And scroll down just a little bit. And so
Mike, isn't the length equal to 5 because we're not including the mid from the last part?
Oh, 1, 2, 3, 4, 5. You're right. I can't count. Thank you. So that should be a 5. And now my midpoint, so 5 divided by 2 is 2.5, but we're using the integer division, so we'll round down and get 82. And I'll go ahead and redraw what the actual list is. I need to be able to see the numbers. -10, -3, 1, 5, and 8. And scroll down a little bit. And so now my midpoint here is 2. This is position 0, 1, 2, 3, and 4. And so here is my midpoint, position 1. And this if statement right here, it's not greater than 1. It's not less than 1. It's exactly equal 1. So we hit this second base case down here where we'll return true because we happen to have found the exact value that we're looking for. So this is another sort of function that has 2 different base cases. Again, it's possible in a recursive function to have multiple base cases, but you must have at least one. And similarly, it's possible to have multiple recursive calls. You just have to have at least one recursive call. So here we finished like really quickly. We were able to find that 1 was in here in just 2 iterations. And you might say, okay, we got a little bit lucky because we happened to land exactly on 1 right here. So let's try a different example where now instead of y equals 1, we'll do, I'll cross it out with green. We'll do y equals 8. And so this first step is going to happen exactly the same way. 8 is less than 16. And so we still go to the left, come down here. But now at this point, our midpoint is still 2, and 8 is now greater than 1. So we'll go to the right. And so we're going to use this recursion right here that subproblem, and our XS equals mid plus 1 colon, like that. So mid plus 1 is 3. And so we'll get positions 3 and 4 that we'll search over. And so that's these two right here, 5 and 8. So we have 5 and 8 at positions 0 and 1. Now the midpoint of this, 0.5, divided, rounded down, gives us 0. So we're looking exactly at that one. It's not going to be present, or it's not equal to. 8 is still greater than, so I'll go over to the right. One more iteration with just the 8. And at this point, the midpoint is this itself. And so we'll get into this test case right here and return true. If we had been searching for 7 instead of searching for 8, then we would still go here, get to this point, get that it's not equal to 8, do one last split of binary search with an empty list, and then we'd get the empty list right here. The length would be equal to 0, and we'd return false. The key thing to observe is just that we started off with a really big, I mean, it's not really big list, but 10 items. It's filling up the whole screen. And really quickly, in just, so one iteration, down to 5 items, 2 iterations, down to 2 items, and then down to 1 item really quickly. So it's by taking away half of the data at a time, we're making a lot of progress towards finding out whether this this value is or is not contained in the list.
I'm sorry, Mike, why did we return false if 8 isn't it?
Yeah, good question. So at this point, let's say our list XS is equal to 8, and we're searching for Y equals 7. Then our midpoint, our length, is equal to 1. So our midpoint is equal to 1 divided by 2, 0.5, rounded down, equals 0. And so indexing XS at position 0, XS at mid gives us this 8. So we'll be comparing 8 XS at mid to Y, 7. 8 is greater than 7. So we'll go into this test case right here, ignoring these two. And when we're in this one right here, when we have :0, the :0, recall that the thing to the right of the colon, we go all the way up to, but not including the thing on the right. So that gives us actually the empty list.
So why was 7 and not 8 then? I thought Y was 8. Oh, sorry.
Yeah, if I do XS at 0, doesn't matter what XS is, that's always equal to the empty list. The question now is here, previously Y was equal to 8. Why did it become 7? Is that the?
Yeah.
That was a separate example. So if Y was equal to 8, then we would hit this case right here and return true. If Y was not equal to 8, if it was equal to 7, then we would do this case right here.
Professor, I have a question. How difficult would it be to like figure out where about in the list that element was, right? For example, like we wanted to figure out like if 8 was at the, index 4, right? Like how, is there a way we can do that through binary search?
So you're saying instead of just returning true or false, returning the index?
Yeah, like, well, maybe like true and it was at this place.
Mm-hmm. Yeah, it's a great question. So with this formulation right here, we can't do it because when we make this copy, we're losing the information about the index. So yeah, with this formulation, it can't be done. We're losing all the information about the index. And that's the reason why this formulation is the one that I recommend that you use for the homework assignments, because the homework assignment will actually require you to return the index. And here, the sort of difference between this version and the one that we just looked at is now, let's see, so there's two differences. One is we have this recursive helper function right here. So this go function is the one that's actually doing the recursion. And it's not this. This function is not directly recursive. It's only recursive because it's using a recursive helper function inside of it. This recursive helper function, rather than passing a smaller list each time, it's actually passing the indices left and right into the main list, into this XS list at each iteration. So left would be your leftmost position, right would be your rightmost position. And so the way this relates to the problem below is that XS in the problem below equals this problem's XS from left to right, like that. So before we were sort of doing the subscripting in the recursion. Now there's no subscripting, it's just keeping track of the left and the right parameters. I can go through an example of actually work through the details of that here in a second, but that's the high level idea. Before I do that, are there any other questions about the this recursive 2 problem down here?
Yeah, Mike, I have a general question about if we want to know whether one thing is contained in the list, why don't we use to test if that number is in that, or why are we using binary search here?
So the question is, why don't you do something like if y in XS?
Yeah.
Okay. So this, if you do this in Python, then that uses the sequential search algorithm. And so that means that it has runtime theta of n, but it's guaranteed to work for all lists XS. And in particular, it doesn't have to be sorted. The advantage of binary search, you have to have things sorted. You must have the sorted list, but your runtime is much, much smaller at theta of log n. And yeah, this is, it's hard to come to terms with just how much smaller this is. That this could, for if Google search were using this algorithm, it would take years to search through the entire web. But using this algorithm, it takes microseconds to search through the entire web.
Can I ask a question?
Hey, Mike. Oh, sorry.
Okay.
You go ahead.
All right. So on the homework, we were using, of those two algorithms, we said O of n for the runtime. What does theta of log n mean when we're not comparing one function to another? In comparison, could we say O of log of n too, or?
So anything that is theta of log n is O of n. So binary search is also O of n. O of log n. And if we were really being as formal as possible, we would say that binary search is something, it's going to have some really complicated formula, one that I can't even create a formula for, but it would have some really squiggly graph that kind of goes all over the place. And so the only meaning of this is that we're simplifying the actual runtime down to something that is smooth, and so we ignore all of these jagged edges.
Okay, thank you.
Hey, Mike, I was wondering if you're given something that is not sorted, is it faster to sort it and then run binary search rather than running a sequential search?
It's a great question. The answer is that sorting, and we'll talk about this next week, sorting takes time. Theta in log in, which is greater than the theta in time that it takes to do the sequential search. So if you're only doing a single search, it's fastest to do just the sequential search. But if you're doing more than one search, say thousands of them, then it's going to be fastest to do the sort first and then do a bunch of binary searches.
Awesome, thank you.
Hey, Mike.
Mm-hmm.
I'm trying to piece together what you had mentioned about Google's search engine. And so if in order to, like, I guess, add a new item, or in this context, like a new website into the web, would it have to take the theta n like sequential runtime to like find its place in the sort?
That's a fantastic question. So, and in some sense, this is the question that we're going to be sort of like grappling with the rest of the semester. The question is roughly, given a sorted list, how can I add an element in the right spot in the sorted location? And the answer is that it's actually fairly complicated. The algorithm that we'll be talking about is called the AVL tree, and it lets you do it in time theta n, which lets you insert in time theta log n. And so with the AVL tree, we'll be able to insert in time theta log n, which is essentially instantaneous, and do queries in time theta log n. And so yeah, we can find things and add things and remove things, basically all the operations that you want essentially instantly with this data structure. So that's the like big thing that we're building up to. There's going to be a lot of steps along the way to get there, and yeah, we'll see that all of them have various incomplete things about them. Good question. Let's see, it seems like we're getting into more higher level questions at this point. So I want to just run through this, a quick example of this version of the recursive binary search, since this is the one that's really important for the homework. And I'll also mention that, let's see, so this one is assuming things are sorted from lowest to highest. In the homework, some of them are sorted lowest to highest, some from highest to lowest. And so you'll really have to be paying attention to that on the homework assignments. And you'll also really have to be paying attention to your like less thans and greater thans, whether they're like less than or equals and greater than or equals to, or where exactly your plus ones are going. Let's see, getting just a rough outline like this will be really quick, but getting those minor details will be the hard part. And the vast majority of problems that people will experience are going to be related to getting this +1 in the right location. And you might be tempted to use greater than and equals or less than or equals, which is perfectly okay, and how I did it. But very like slight off by one sort of edge cases that you'll run into. Okay, so let me delete this up here so we can see the whole program at once, and I'll need to delete that as well. And let's scroll down there, and let's have, so let's see if I remember it's probably not going to be the same exact numbers as before, but that's okay. 3, 5, 8, 15, 22, 33. Those will be our numbers this time. And our positions at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have a list of length 11 at this point. And this is our XS. And we'll do a search for, let's see, we can write it right here. Y equals, we'll do 9. So we'll find something that's not in the list. And so at the very beginning, we'll call go with go starting at position 0 to the end of the list. So our left will be here, and our right will be here. And so first thing, we have our base case check up here, and then our midpoint calculation, left plus right over 2. So right is 10 plus 0, 10 divided by 2, 5. So that's our midpoint right here, right in the middle. And then we'll look at XS at mid. So this spot right here, that's a 3. That's less than the 9 that we're looking for. So we are in this situation right here, that XS at mid is a 3, Y is a 9, so 3 is less than 9. And so we're going to change left to be mid plus 1. I'll do this in red now. So now here will be our new left. And our right will stay the same over here. And so this is the sort of sub list that we're looking in now. And you can see that we still sort of chopped off half of the list. So that's sort of the key thing about binary search. It's not necessarily the syntax that you're using, it's just that you've eliminated half of the search space in each iteration. And how you keep track of what half of the search space is that you're looking through kind of is an implementation detail that's not super important. The important thing is just that we've somehow eliminated half of the possibilities from consideration. And so now in this iteration, 6, we're going to find our index that we're looking for. 6 plus 10, doing this midpoint calculation right here, left plus right over 2. So 6 plus 10 divided by 2 is 8. So that's this position right here. So that's our midpoint. And so now it's the 15 that we're comparing against the 9. And the 15 is greater than the 9. So we're in this first if statement right here. And this is 15 again, and that's 9. And so what we do is we set the right point equal to the midpoint. So let's switch to orange. Our left will stay the same, but now this is our right. And our midpoint, 6 plus 8, 14 divided by 2, 7. And so that right there is our midpoint. And let's say we originally started talking about this version of the problem because it was asked, how do you keep track in the original, like indices in the original list rather than in our modified sublist? And you can see that all of these numbers that we're working with are staying indexing into the original list rather than the modified sublist. So if, like in the homework problem, you need to actually return the index, then you need to use this style of keeping track of where you are in the list. So here, we're looking at 8, comparing 8 to y. Y is 9, so we compare 8 to 9. 8 is not greater than 9, 8 is less than 9, so we're in this situation again. Left equals mid plus 1. So our left and our right are now equal to each other. And right here, we have left and right. both pointing to this same index location right here. That puts us into this base case, and we check, is this position equal to what we're looking for? It's not. This position is 15. 15, we're looking for 9, so we'll return false. Any questions about that?
I have a question about, I think it may have been the third iteration of this code. I remember in the previous example, we omitted the midpoint we were looking at in like the sub list, and I'm wondering why we're not doing the same in this function.
I'm not sure what you mean. We omitted the midpoint we were looking at.
So in the red line, that sub list, we checked 15 as the midpoint, and then when we like made the comparison to the y value, we like kept that in the orange list that followed rather than omitting it.
Yeah, it's a good question. So let's see. This is getting into, let's see, there's a couple of ways to answer the questions. One is that I think it just happens to be the way this code is written, that when we looked at this orange list right here, we kept the 15, this midpoint. So this was specifically on the red one, we were comparing the midpoint against 9. So excess at mid is greater than 9, 15 was greater than 9, so we used this one right here. And actually, yeah, so what I have here is right equals mid. You're right that I could have changed this to be, it is. So 164 to go to line 164, capital A to go to the end of the line, -1 like this. And we know that, in fact, because they're not equal to each other, we don't have to consider the midpoint, and we could have put -1 here, and that would potentially make the code like tiny bit faster because it doesn't have to check this midpoint as well, and it would still be correct. This is one of those, I guess, issues that I'm sort of referring to in the off by 1 errors, that it's really easy to have your code somehow be correct or incorrect with subtle differences in these sorts of formulations, exactly what you put here. And yeah, there's essentially no difference between having it there or not having it there. Very slight minor runtime difference possibly, but no correctness difference. Did that answer your question, Jonathan?
Yeah, thank you.
So yeah, similarly, I guess whether you have these -1s and +1s is going to be related to whether you're using less thans and greater thans, or less than or equals and greater than or equals to. If we had changed this to be greater than or equal to, then in that case, I would have to not include this, this -1 right here. Yeah, so with binary search, there's lots of ways to write correct code, and it's still correct, and there's no preference about one over the other. Any other questions so far? Okay, then now's where we're going to start getting into the the brain bending mind explosion part, and talking about the actual runtimes of these algorithms and how you go about proving what the runtime of binary search is going to be. And since this code on the bottom down here is a little bit shorter, this is the one that we're going to do the runtime analysis for. And so for a recursive problem, we're going to write our runtimes using what's called a recurrence relation. And a recurrence relation is just a formula that is a recursive formula. So typically we use the T of n. Oops. It's just traditional to use the letter T of n to be the runtime of whatever function it is that you're analyzing. And the reason T is traditional is because it stands for time. And here n, again, is the length of my input list. In this case, the length of XS. And we're going to write our runtime sort of in terms of, or we're going to write the runtime of this algorithm in terms of the runtime of this algorithm. So the first thing that we'll do is have a base case for our recurrence relation. Anytime you have a recurrence relation, the formula is going to look something like, you'll have two cases, and the first case is pretty much always going to be a constant. So I'll write 1 here, or you could write theta of 1. Often when people are writing recurrence relations, it's just implicit that there's a theta in front of everything. In the future, I might not put this theta here, but it's implicit theta of 1, and that's my base case for when n is equal to 1. And since n is equal to 1, it in some sense doesn't even matter what the formula is here because n is a constant, it's not a variable, and so we just plug in 1 for it and it simplify it to a constant and get a constant value, theta of 1. So the base case is always theta of 1. And there's our base case. So now down here, we have to think about what's the runtime of each of these lines. And so this line right here is going to be constant runtime, taking the length of a list, constant runtime, indexing into a list, constant runtime, then checking to see whether two things are greater than or equal to, also constant runtime. So O of 1. And here we have two operations going on. So I'll separate these out into two different things. We have the slice equals XS at colon mid, and then passing in the slice to this function call. For a list, the slice operation, this slice operation takes time O of k, where k is the size of the slice. So O of k, where k is size of slice. In this case, the size of the slice is n over 2. In this case, so the runtime would be O of n over 2, or just O of n to simplify. And then the runtime down here is going to be T of n divided by 2. So T, because that's what we said is just going to be the runtime of our algorithm, and n over 2 because the slice is half as big as the original list. This n over 2, it's important that this n over 2 here is not in asymptotic notation, and so this constant factor does in fact matter. So not asymptotic or big O notation, so the 1/2 constant factor matters. And then for this is going to have the exact same runtime as this up here. It's the same exact operations, just slicing in a different way. So that one's O of n, that one's T of n over 2. Here, constant runtime, comparisons is constant. So we have O of 1 and O of 1.
Wait, Professor, isn't the if statement O of 1 too? Not O of n.
Thank you, yes. So this is O of 1, and if we were to split this up into slice equals excess of mid plus 1 colon and slice, then there we go. Then this is the line that's O of n. Yes, that is correct. Any questions about just how individually any of these lines are working, getting these numbers?
I have a question about the t of n divided by 2.
Mm-hmm.
The n divided by 2, is that what we got from the slice that we're putting in as a parameter in the recursive call?
Exactly. So the length of slice is the length of slice, this should be a comment, is n divided by 2. And the runtime of t is whatever the length of the input variable right here is. And so that's why I'm using n over 2 as the parameter.
And this is not, like, the t of n divided by 2 is not the notation for the overall function. That's just the notation for the recursive call.
So this t and the t for the overall runtime are the same thing. Maybe that'll be clarified once I sum all these things together and get our final formula for the runtime of this, this function here. So let me go ahead and do that. So our rule for when we are, we have code that happens one after the other is that we add everything together. And so that's what we're going to do. We're going to add all of these things together. All of the O of 1s will just simplify down to stay at O of 1. And here there's one other slight trick that we know that if this if statement gets executed, then this if statement is definitely not going to be executed. So we can ignore one of these if statements and just treat it as like there's only one of these included. And so our final runtime is going to be t of n. So this is the n for the input, the overall input is going to be t of n over 2 from this, plus we have all of these O's of 1s up here, O of 1, but then we also have this O of n right here, plus O of n, like this. And that would simplify to, let's make it in the comments, t of n over 2 plus O of n, where this constant right here gets absorbed into this linear factor there. And so this is my recursive recurrence relation runtime for this function. Are there any questions about that?
These may be things that you'll discuss in the next few minutes, but I have a question on how we would translate that into like the bracket that you have down in the drawing pad. Mm-hmm. And also, I feel like my understanding of binary searches was that it would be reduced to like O log of n. And so I'm wondering like when that's going to step in.
Yep, good questions. So first, where does this play into this? Down here. This equation that I wrote right here is what you put down in this sort of bottom half of the recurrence relation. So t of n over 2 plus, and I'll just drop the asymptotic notation and put just in here. And this is for all of the non-base case situations. Because the base case is always just constant like this, you'll frequently see people write the recurrence relation as just T of n equals T of n over 2 plus n, with the implicit knowledge that the base case is 1, the base case of this function is 1. But this is sort of the more technically correct way of writing this expression down here. So that's how this relates to this. And now there's a question of how do we actually translate this right here into a sort of a normal simplified runtime that's not a recursive runtime. So we want to simplify this. Simplify so that there is no t on the right-hand side. And the tool that we use for that, and we'll be using it a lot over the next couple of weeks, is called the master theorem. And it is called the master theorem because it is the tool that is used for analyzing the runtime of everything. It is a general theorem for analyzing any function that is like a recurrence relation like this. And it just happens to be very widely applied in computer science for analyzing runtimes. But there's nothing in the statement of the theorem that says it has to be about analyzing runtimes. This is just a function, just like random functions that you were looking at in calculus or linear algebra or differential equations or any other math classes that you might have taken. And you can use the master theorem to solve these functions, simplify them so that there's only one occurrence of the function instead of two. And that's what we will look at next, is how do you do the master theorem to simplify these functions. Let's see, this is relatively, the theorem itself, maybe I'll just switch over to Wikipedia right now. We'll be using Wikipedia's version of the master theorem. And, oops, that's the wrong thing. If you come down onto the course lecture notes, there's a link right here to the master theorem. You can click that. And after it loads, it takes us to Wikipedia's master theorem page. And the statement of the theorem is this giant block right here. This entire thing is the statement of the master theorem. So probably it is, even for those of you who are math majors and have taken lots of math courses, this is the biggest, most confusing theorem that you have come up against in any math class. And so we're going to spend a lot of time focusing on exactly the details of this theorem and how to understand it and exactly what's going on. We're not going to talk at all about the proof of this theorem. That proving this theorem would be that's like an exercise for a second or third year graduate student taking combinatorics courses to do. So not at all in the realm of things that we have the tools to use to prove it. We will just be applying this theorem to our problems. And yeah, so see, we're not going to have enough time today to fully talk about this theorem. So I'll just point out that up here you can see something that looks kind of like the equations that we came up with before, where we had this T of n function appearing on the left and T of n appearing on the right. Here it's not just T of n, but n divided by something. And somehow, anytime we have our recurrence relation, we're going to pick a value of a and b and f so that this formula right here equals the relation that we've come up with. So I'm going to adjust my screen like this so that we can see, there we go, both the formula and our results over here. Zoom in on the right-hand side. So this is the expression that we're trying to find. This is the expression that we have, or this one right here. And if we set a equals to 1, b equals to 2, and f of n equals to n, then this equation right here would be equal to this equation right here. That's sort of the key conceptual step that you need to be able to do in order to get from the runtime analysis of a function, of a program, into something that can work in the master theorem. That in the master theorem, all the conditions are about this A and this B and this F. And so you have to first be able to convert things into this form like this. Then once you have something in that form, there are conditions on what the F's and the A and the B satisfy. So there's, zoom in a little bit. There's this value C crit. This crit stands for critical. And C crit is equal to the log base B of A. Log base B of A, which in this case, log base 2 of 1, which is equal to 0. Log base anything of 1 is equal to 0. So our C critical is equal to 0. And then our F gets matched up into one of these 3 cases right here. And let's see, actually determining which case that you go into, it'll become second nature eventually, but you can see that there's big O's and thetas and omegas, and so you'll have to be really paying attention to the subtle differences between each of these asymptotic notations. And it is very subtle. I think we are out of time for today's lecture, so I'm not going to go into the details of doing it for this problem at this point. We'll pick that up on Monday, but this is not going to be important for your homework assignment and getting your code actually implemented, as long as you sort of understood the walkthrough of the functions themselves. Then you'll be able to implement the binary searches, and starting next week, we'll pick up again with using this master theorem to analyze runtimes. So that's going to be our official end of course for today. I'll stick around, have office hours now, and answer any questions that people have about this or anything else. But otherwise, I will see you on lab tomorrow or Monday next week in class.
Thanks, Mike.
See you then.
Mike.
Thank you.